SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course, that is Power Plant System Engineering, module number 4, and this title of this module is Hydro and Renewable Energy Power Generation Systems. So in this module with lecture number 8, our main focus would be energy storage, and this lecture, which is the part 1 of this module, we will talk about the two basic units of energy storage systems, that is pumped hydro storage systems and compressed air storage systems. So basically speaking, both these storage systems have same philosophy, but only difference lies is there. In a pumped hydro systems, we have the storage medium is water, whereas in compressed air storage systems, your storage medium is air. But before you start, let us try to understand why we require the storage. In our previous sections and modules, we have seen that renewable energy systems comprises of wind energy, tidal energy, geothermal energy, solar energy, and those energies are intermittent in nature. But if you look at the energy demand in terms of electric energy in a utility systems, they vary hourly, daily, monthly, yearly, and so on. At the same time, the energy supplied or available for generation of electricity is also intermittent. So it is very difficult to map when your demand is high or demand is low, or when your supply is high and supply is low. So to counter this effect, we require some kind of mechanism in which energy can be stored with a philosophy that when there is a demand, the stored energy can be utilized to cater the needs. So the very basic need of energy storage is applicable for renewable energy systems, that is solar, wind, ocean, tidal, where output of the plant also fluctuates. So to address this power intermittency, which is a situation where we cannot provide the power based on the demand, which is normally the case when we have a conventional plants operated with a fossil fuel or a hydropower systems. But to some extent, these things can be countered for renewable energy systems with a mechanism of energy storage. So hence the need of energy storage becomes inevitable for renewable energy systems, mainly to counter the fluctuations in demand for electricity for assuring a steady output. So it operates with a fact that when the demand is lower than the capacity, energy has to be stored. When the demand is higher than the capacity, the stored energy can be released. So through this process, we can have supply of electricity in a reliable manner, efficiently, and in most economical way. So in a larger sense, if you see earth crust where natural energy is available, they are also quantified in the form of fossil fuels or inert metals, and earth also we can say the largest resources of energy. So to give some quantification numbers, energy available or energy density in terms of with respect to fossil fuels, it falls in the range of 14 to 10 to the power 6 kilojoule per meter cube area, whereas from nuclear materials the energy resources can be the order of 10 to the power 14 kilojoule per meter cube. So, we have been using this energy from millions years of existence of human existence. So, but at the outset when you say that current scenario the energy crisis is significant, so we require a storage medium. So, this is a sample plots that talks about why we require a storage systems. First thing, the first plot talks about a case where energy or power which is available from solar incidence from throughout the day. So, if you look at the supply, supply is very specific, but means in the form of solar energy which is available mainly on daytime, and so we can there is a supply, but demand also varies in a natural way, but in some cases we can see that supply is less but demand is high, and in some cases if you take the peak value of the supply and take an average line, then we can say that solar energy cannot continuously supply as per the demand. So, the to counter this effect, one another situation that can be plotted in for a power in terms of for a fossil and nuclear power plant, we can say that the nuclear and fossil fuel based power plants, they supply the constant available power throughout these things. They are quite capable of supplying this power as per the need, but when the demand is higher, we cannot these plants cannot be in a position to cater the need for peak demands. So, for that reasons, when there is a continuous generation of power, we can store them, and during peak demand period they can be discharged. So, that is the idea. During peak demand the energy has to be supplied from the storage, and during normal situations it can the fossil fuel power or nuclear power plants, it can cater the base load operation. So, if you look at the energy storage mechanisms, we can say that if you say start with a primary heat source and we want to store it, it can be stored in an electrical storage manner or it can be in a thermal storage manner. So, let us start with this line, that electrical storage. So, when the conventional plants run at a base load operations and we get the electric power from its generating stations, sometimes you can these plants can give a base load operation or base load, but at this similar situation we can also have the excess electricity. So, that excess electricity can go to the storage. Now, this storage have the possibilities that we can have electromechanical systems or direct storage, and electromechanical systems can be further subdivided in the form of storing in the form of potential energy or in the kinetic energy. Now, looking at the potential energy, it can be stored as a pumped hydro medium, or it can be stored as a compressed air medium, or it can be stored as a torsion bar, springs. This is what we say potential energy based storage, and it falls under electromechanical systems, which is a combination of mechanical and electrical energy. Other part, it can be a kinetic energy based systems where this energy is stored in terms of flywheels. So, typical example of this flywheel normally is that we use in a conventional IC engine based plant or engine. Other kind of things which is a direct storage of electrical energy, it comes in the for storage batteries and superconducting magnets. Now, if you look at the thermal storage based systems, the load inputs can also go directly to the power generating stations to provide the base load, and the excess heat that can go to thermal storage. So, these storage things can be possible through sensible heating storage, latent heat storage and chemical reaction storage. So, for all the cases there are two basic important inferences. First, the primary plants run with a base load, and excess electricity which is stored energy which is used as a peak load. Now, even in thermal storage also the primary station runs for base load and the excess heat which is stored in the thermal storage medium, it runs for peak load. And this is how the curve looks like, that for a continuous throughout the day, if you want to have a steady power, so during normal situations, so anyway we are getting a steady power. So when the during off peak hours energy can be stored. Now during the peak hours the stored energy can be released. So if you take the average of entire day, so you can say that it is a steady state operations. So this is what I have explained, that we have electrical and mechanical storage types and flywheel energy type and batteries, superconducting coils. So in our subsequent discussions, we will be talking about mainly on compressed pumped hydro storage, compressed air storage, flywheel storage, then storage in batteries, that is in the form of electromechanical storage. Now, moving to the thermal energy storage systems, we will talk about this latent heat storage, sensible heat storage, latent heat storage and chemical reactions. So, we call these schemes as thermal storage schemes in the form of sensible heat, latent heat and chemical reactions. So, the first point or first storage systems of our discussion is a pumped hydro storage systems. Now, we all know that, or in our previous modules we have discussed, not in the previous module, in fact in our first lecture, first few lectures of this module number 4, we have talked about the hydro power systems, where the power generating unit, by converting the potential energy of water, and that energy is getting imparted in kinetic energy mode to the turbine rotor. So, that way this is what we say or talk about a large scale plants. But what happened is that now in a pumped hydro storage systems also operate in a similar manner, but main difference, because in our previous study it was only the power generating mode, which means that turbine and generator are coupled, which is in a hydropower systems. But in a pumped hydro storage medium, that means first we need to store the energy in the form of potential energy and with water as a working medium. So, that potential energy can be used to cater need during the peak demand. That is the entire idea. So, for that purpose, what we require? We require a pumping unit that will pump, that will be integrated with a power plant. When there is a excess power available, that excess power can be utilized as a pumping mode, that means to pump water from a lower reservoir to a upper reservoir. This is what we talk about a pumping mode. And during turbine, during discharging mode or during peak demand, that same energy can be released, which is similar to operation of a hydropower plant, and that is called as power generating mode. So, we have a pumping mode, we have a power generating mode. So, that way one can say that to store the energy in a pumping mode, we have head available, or pumping mode head is H is equal to HP minus HLP. Since it is a pumping mode, this is what talks about the losses during flow conditions of pumping. Now, when you when that hydro storage energy runs in a turbine generating mode, we have the head available in the turbine and head losses during the most operation of turbine mode. So, that losses comes by virtue of the length at which the water flows in the pipe, and the pipe means it is something like, which we call this as a penstock. So, what happens is that during pumping mode we have the height travelled by the water is h, and during turbine mode same height is there, but main thing is that here heads are different. That means losses during pumping mode and losses during turbine mode can be different. Further, turbine may not operate for continuously. It is, suppose we are doing the pumping mode for 8 hours, but turbine can operate for 2 hours. So, that way the controlling factor of H and HT is different. So, based on this we have different flow rates for QP for flow rate of water for pumping mode and flow rate of water during turbine mode operation. So, that with other words means that head is converted to power for pumping mode and for turbine mode. Now, to make this concept effective, we need to have two reservoirs, one is upper reservoir or other is lower reservoir. Now, these reservoirs can be naturally generated or it can be artificially generated, or you can create some kind of artificial reservoirs. So, one case it can be a lake, river, natural river. Other things we can artificially exhibit some of the reservoir. To make this effective, we have two important things. First is elevation height H, which is defined either for pumping mode and turbine mode. Other is the maximum horizontal distance. So, basically, so H is detected by this height and length, which is the actual length in which the water flows in the pipe or penstock. So, that L by H ratio when it is less than 2, then it makes sense that a pumped hydro storage systems can be effective at a particular geographical site. Now, next thing is to give more insight to pumping pumped hydro storage systems. We can have high head installations in which we can have upper reservoir and lower reservoir with have a steep slope. Other case can be a medium head installations. It can be a horizontal open canal with a short pressure pipe for towards this powerhouse. So, these two things are very are mainly necessary to justify the requirement of a pumped hydro storage systems. And most importantly, topography of a geographical site is also important. Many a times pumped hydro storage systems can be also considered above ground or underground. So, above ground means that it like lower reservoir. If your lower reservoir is on the surface, so this upper reservoir will be above the surface at certain height. Now, other way we can say that beneath our ground we can create a low reservoir, because once you go to a depth, then we can create a underground reservoir where water can be stored and they can be easily accessible. So, so that is another way we can look at in looking at the topography. Now, there are some situations in the earth crust we can have a natural caverns, mines or underground cavities. So, those locations can be effectively chosen to store our water. So, that is the idea, the pumped hydro systems that operates. Another important part of this I have already mentioned, that excess energy supply which is occurs when the pumped hydro systems operates in the motor generator mode, and during the storage phase the pumped hydro systems operate in a the pump hydro systems operate during storage pump motor systems, and during generation phase it operates in turbine and generation mode. So, which means that excess energy supplied by the primary plant during off peak hours can be used to drive a motor pump to elevate water from lower to upper reservoir, and during peak demands the system can reverse the turbine generator mode for producing the excess electricity. Now, there is a method in which the efficiency or efficacy of this pump storage system is defined, and this combined efficiency for pumped hydro systems we called it as turnaround efficiency. So, basically there is a charging period and discharging period, and it talks turnaround efficiency talks about how much we have charged, but how much we have actually discharged. So, taking into account the power produced during discharge phase and power produced during charging phase, the turnaround efficiency falls in the range of 62 to 68%, which is a quite reasonable number for any energy storage devices. But main issue is here that when you talk about storage, their energy densities are less. So, you cannot supply continuously for a long run. So, it is only used for peak demands. Now, we will move on to next segment of our discussion, that is compressed air storage systems. When you say pumped hydro storage, it takes the advantage of hydrostatic pressure to increase the potential energy of water through its elevation. Now, the analogous mode in the compressed air storage is that energy is stored in the form of reservoir, aquifer or caverns, and this stored energy is released during the period of peak demands by expansion of air through an air turbine. So, essentially in a pumped hydro we require a hydro turbine, but in a compressed air storage we require an air turbine, and water is liquid phase and air is a gas phase. So, in both the cases in the first case we are storing the water in a potential form. Here also we are storing the potential energy by compressing the air in a compressed form, air in a compressed form, and there, but another additional feature that we have, during this compression period temperature of air also increases. That part gives an additional advantage. Now, looking at the storage, compressed air storage systems can be of three types. One is salt caverns, aquifers or hard rock systems. Salt caverns are most stable compressed air systems, storage systems, because of its loading for entire duration of the plant life. Aquifers are naturally occurring formation of porous rocks that has capability of air water interface movements. So, that pressure difference can be utilized as a storage. Hard rock systems maintains air pressure above its surface, but main difference is that this system is not stable when we have large temperature fluctuations. So, however, our main intention of this compressed air storage systems will be talking about salt cavern systems, which is a more stable systems and simplicity in its operations. Now, how a compressed air storage systems in salt in a cavern mode looks like. So, what we have shown is this figure is a hybrid mode of systems. Hybrid mode, I mean when we compress the air, both pressure increases as well as the temperature increases. So, which means we are storing its the stored energy is in the form of pressure as well as thermal energy. So, that way it is a hybrid mode, and the system is mostly adiabatic because we do not allow, because we are taking out the heat from this compressed air after its compression. So, and we are not allowing this heat to go out of this thing, out of the system. Now, how it operates? Let us see this figure. So, what we see here is that a motor generator set MG, and it is coupled with a compressor one side and turbine other side, and this turbine is nothing but it is a air turbine. Okay. Now, what happens during off peak hours, that means when we have excess that energy is there is not much demand. So, what we do is you run this unit, that is motor generator unit, as a motor mode. So, when it runs as a motor mode, it runs this compressor. So, during when the compressor is starts running, air gets sucked into this compressor from atmosphere. Now, once it comes during this process of compressions, its pressure, temperature increases. Now, when it enters, now we are storing these things in a underground reservoir or reservoir R, which is called as air storage reservoir. Now, before entering this air reservoir, we allow this compressed air to pass through a packed bed storage material. So, here we have some materials that can absorb the heat from this high temperature air. So, when by absorbing the heat is retained within this packed bed, and once it goes and during its during this charging phase, what happens? Energy we capture, thermal energy we capture through the packed bed, and this low temp what you say, when this temperature drops, after through this process your pressure does not change, but temperature drops. So, normal air is gets stored in a reservoir, we call this as a air storage reservoir. Now, this can be underground as well, or it can be kept in a balloon or some cavities in an underground systems. That is a possibility, we call this as a cavern. Now, during discharge phase or during peak demand, we allow this MG set, that is motor generator set, to operate through turbine mode. So, it means that compressor mode is switched off and we side by side start the discharging mode. So, through this process the compressed air by virtue of its own pressure again passes through this packed bed. Now, during this passage through the packed bed, it absorbs the heat which is stored inside this packed bed material, and again its temperature also increases. Now, why and when after that things the high pressure and temperature air we try to expand in the turbine. Now, why do you require this thing is that we expect that during expansion phase air should not condense. So, that is the idea, that it should not condense, and that means when you allow this air to enter into this turbine, its temperature is reasonably high enough, so that during its expansion phase it does not condense. So, through this the system operates. So, this is how the system operates, and which is a single stage adiabatic compressed air storage systems that operates during a charging phase and in a discharging phase. Now, typically since this system operates in a adiabatic manner and we are talking about a very high pressure and temperature storage, conventional system of talking about gamma Cp value, that they do change. So, for that case, instead of assuming a isentropic systems, we call this as a polytropic systems, and these polytropic systems operate in a adiabatic manner. Now, during the polytropic compression, we can find out this temperature ratio, that is T2 by T1 as pressure ratio raised to the power n minus 1 by n. N stands as index of compression. Then to get the efficacy of the systems, we also have to consider the storage capacity of the reservoir, and we call this as a and this has to be quantified as a storage efficiency, and that storage efficiency operates in an adiabatic manner, and we call this as a adiabatic storage. First thing. Second thing, the system is also a hybrid system, because we talk about thermal as well as pressure energy, which is tapped simultaneously during this compression phase. Now, if you look at a typical workable model for an hybrid adiabatic systems, one can say that a cavern size or talks about the storage volume, and first thing we need to quantify what should be this cavern volume, and based on the cavern volume, it will be the size of the packed bed thermal storage will be 10% of that number value. So, a typical situation for a peak unit capacity of 1500 megawatt hour, a expected storage would be 20 lakh meter cube volume of storage capacity to store 10 bar pressure. So, which means that if you want to store a 10 bar pressure, store air at 10 bar pressure to for producing 1500 megawatt hour energy, then you require 20 lakhs meter cube storage area. So, which is a huge. So, this is not a feasible options. So, what we have to look for is that we have to look for a higher storage system medium. So, we have to store the air for same capacity at higher pressure, and so that our volume reduced or storage capacity reduced drastically. So, 20 lakh meter cube comes down to 64,000 meter cube, which means at higher pressure the storage volume is less, which means that your cost of developing this system will be less. Hence, it is concluded that a compressed air storage systems becomes effective when we have when we are exploring high pressure storage system. Now, additionally, what happens, there are techniques like we have already told about the single stage compression, single stage expansion, multi-stage compression and multi-stage expansions. So, one way we can think about, instead of compressing it in a single stage, we can think of multi-stage compressions. So, this is a case of 3-stage compressions, and this is a 3-stage expansion in the turbine, and everything what we do is a air compressor and air turbine. Let us try to see that if there is any workable model which is available in a compressed air storage systems. So, the first compressed air storage systems was designed and built at Brown Brewery in 1978. So, it is a hybrid gas turbine plant which is built at Hernhof, Germany for a capacity of 290 megawatt. Now, to cater this is shown in this figure. Now, to cater this need, what the cavern requirement is 3 lakh storage volume. Storage volume capacity is close to 3 lakh meter cube, and this is created with by leaching in a leaching salt dome, because normally we keep this salt in these things because its density becomes higher and higher. So, in the leaching salt dome, the air is stored to increase its density, and this is stored in a depth which is 650 to 800 below this ground. It is not an underwater, rather it is a underground. Now, while this is what we do in a charging mode. So, in a storing mode, compressor pumps the atmospheric air into cavern and stores at 50 to 70 bar, and in generation mode we do not operate at 50 bar, we operate at a less pressure, which at a reduced pressure, to maintain the pressure, constant pressure in this storage volume. So, it is operated at lesser pressure 46 bar. So, this is a case where atmospheric air is taken at 10 degree centigrade, and it is a 3-stage compression and or 3-stage compression and 2-stage expansion. So, additionally we have other units like intercooler, aftercooler at various locations. So, this is just this particular figure just to give you a feeling that such a compressed air storage system do exist and it is integrated, it has to be, of course, it has to be integrated in any one of the power plants. In fact, this particular unit is a hybrid mode, operates in a hybrid mode, that is with a packed bed, and it is a gas turbine plant. So, other point is that for this particular unit, it is the storage occurs for about 8 hours, but generation occurs is done only for 2 hours. So, that thereby we maintain a constant pressure in that air storage reservoir. So, this is all about this compressed air storage systems, which is a very fundamental requirement for any kind of power plant operations, and it falls as a renewable energy because we do not spend any extra cost for this developing the systems. So, we are just taking the excess amount and try to store it, and this unit is only gives the peak requirement of demand. Now, with our discussion today, we will try to solve a numerical problems, which is a simple numerical problems, just to know the filling of the quantitative numbers that we are talking about. So, this problem is about a compressed air storage unit, and which is supposed to be designed and for a charging period of 7.5 hours. That means, we need to charge these things for 7.5 hours. And initial temperature of air is 1 bar 20 degree centigrades, exit pressure is 100 bar, polytropic efficiency for compressor is 70%, and that peaking turbine, here you will not use word turbine, here we will use the word as a peaking turbine, because the turbine runs during the peak demand. So, we need to find out temperature of air after compression, polytropic exponent, storage volume, and average air flow rate during charging. Now, to solve the problems, so let us first understand what as data has been given. Compressor efficiency of isentropic or polytropic efficiency of compressor is 70%, and peaking turbine efficiency is 60%. And initial case P1 is 1 bar and T1 is 20 degree centigrade, which is 293 Kelvin. P2 stands as 100 bar. Now, with this number one can try to find out if had this base efficiency been a adiabatic efficiency, what should I write is that, taking this efficiency as adiabatic efficiency, I can write the expression as H2S minus H1 divided by H2 minus H1. Had this polytropic been an isentropic efficiency, the expression would have isentropic enthalpy difference to the actual enthalpy difference. Since the working medium is air, so Cp gets cancelled, so H becomes Cp times T. So, this equation now reduced to T2S minus T1 divided by T2 minus T1. Now, here and that value if you take, this is 0.7. Now, here known condition is T1 is known. Now, T2S can be calculated by using isentropic relation. T2S by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So, take gamma is equal to 1.4, P1 and P2 by P1 is equal to 100, T1 is already known. So, this will represent this will give you T2S as 1090 Kelvin or 817 degree centigrades, but T2S we do not require, we require T2. So, from this equation we can say T2 is equal to T1 plus T2s minus T1 divided by this isentropic efficiency value, that is, if you put the number, it is 1159 degree centigrade or 1433 Kelvin. But when you calculate this T2, this is based on the absence temperature with this temperature after compression by assuming this number, but what polytropic efficiency it would be. Now, for example, if you say T2 is this, now if you take another expression like polytropic expression for this, so we write P to the power P1 to the power n minus 1 by n is equal to T2 by T1. So, this is polytropic compression. So, if you use this expression and putting this value of P2 by P1 and T2 and T1, then this will give you, this will be 1159 plus 273 divided by 293, which is T2 by T1 is equal to 100 to the power n minus 1 by n. So, by solving this, we say n is equal to 1.53. So, we get the first two answers. What is the temperature after compression? Temperature after compression is 1152 degree centigrade. Polytropic expansion, polytropic compression is index of polytropic compression is 1.53. Now, next part is, so this is A, this is B part, and C part we are trying to see what is the storage volume. Now, to find the storage volume, we need to use the equations which is called as equation of state, which says P capital B is equal to mRT. So, in this equation we know pressure, we know temperature, we do not know mass, we also do not know volume. Now, to calculate this mass, first thing mass calculation, we have to see that what is, we have to look into the requirement for turbine. So, we say turbine mode efficiency is 60%. So, we say that and the WT is equal to 1500 megawatt hour, and if you say turbine is 60% efficient, then this implies your storage power should be 1500 divided by 0.6, that is 2500 megawatt hour. And this 2500 megawatt hour has to be stored through heating. So, for that reason you can write that M mass times specific heat into T2 minus T1 is equal to, should be equal to PS. Now, here we are talking about pressure about 100 bar, and this is close to about expected temperature would be around 1200 degree centigrade. So, for this case we say Cp, variation of Cp can be assumed to be 1050 joule per kg Kelvin. Also in this situation we can also write R is equal to 284.75 joule per kg Kelvin. This data can be obtained from any of the conventional thermodynamics books. So, looking at this, we have we can say M can be calculated as PS divided by Cp times T2 minus T1. So, PS is in megawatt hour, so we have to convert it, that is 2500 into 10 to the power 6 into hour means it has to be in second. So, multiplied by 37600, Cp as 1050 and T2 minus T1 is 1159 minus 20. So, this gives you the mass of air requirement 7.5 into 10 to the power 6 kg. Now, once you know this mass, then we can say what should be volume. So, volume can be represented as m r T by P. So, that is equal to 7.5 into 10 to the power 6, R is 284.75, T stands as atmospheric air, that is 293, P is equal to 100 bar, which is 10 to the power 7. So, all these things converted into Pascal. So, considering this and calculating this, we can say V would be 62575 meter cube. So, for this storage at this 100 bar 1500 megawatt storage at 100 bar, we require a storage volume of 62,575 meter cube. And last part of this analysis is that what is the average flow rate of air into the cavern. So, during charging. So, basically our charging period is 7.5 hours. So, average flow rate so we can say B average as 62,575 divided by 7.5. So, this turns out to be 8343 meter cube per hour. Okay. So, this is all about this problem, which is based on this compressed air storage unit. So, with this I conclude this lecture today. Thank you for your attention.